Before I introduce Daniel Sigman, let me make a request from you. There are pieces of paper and pencils going around, if you want some for them. We're interested in having either topics or the name of people who are faculty members interested who would like to hear in this seminar series next year. Again, the goal for us is to have a wide variety of faculty members doing seminars on all parts of the university, as long as it's somewhat connected to the Antarctic in wide sense. And so we're interested in different ideas and those we can generate ourselves. If you have ideas, please put them on a piece of paper and see the piece of paper outside on the table. Thank you. It's my pleasure to introduce Danny Sigman. I've known Danny for a long time, longer than he wants to know. He was an undergraduate at Stanford University, and then did his PhD in the Woods Hole MIT Joint Program in Oceanography. I could ponder the idea that Woods Hole is actually an institution, so MIT is an institute. I'm not sure what that means, but I'm sure it's a very profound problem for Danny to be both an institute and institution. Danny has had a very successful career. He's very young. He started early in his career here by getting a fellowship from the MacArthur Foundation, was known as the Genius Fellowship, and he's never looked back. Danny is interested in the important problem of the connected cycles of nitrogen and carbon in the ocean, and the related problems of carbon dioxide exchange between the atmosphere of the ocean, primary production, and also all those issues during modern time, but also during glacial interglacial cycles. You hear about that today. During his PhD thesis, he actually invented a new technique to measure exquisitely the level of isotopes discrimination in nitrogen compounds in the ocean. That technique is heard of by him, by a number of his students and postdocs all over the country now, all over the world. And I think you need to hear about that. Danny? No.
Hello, everyone. I'm very glad to be here, but I have a fever, and so I'm going to do a lot of leaning during this talk. The good news is I'm somewhat removed from you. So what I'm going to be telling you about today has a larger context here. We're trying to understand where climate and the environment are going into the future. And for many of us in this room, that means that we are very busy studying the modern environment, modern climate, trying to uncover all the processes at work. This is critical work. This is the only way we have a really robust and detailed understanding of environmental processes, of how physical, biological, and chemical processes give rise to the environment that we're in. And we try to take all of these processes and incorporate them into theories and numerical models that we can then use to make predictions about the future, or at least to imagine what outcomes we would expect for given courses of actions by humanity. But this is actually a pretty hard way to go. Building this theoretical framework from only modern observations, hoping you're capturing everything that's important, hoping you're not studying things that aren't important, this is really challenging. And so an important complement to this is to use the geologic past, the non-instrumental past, to tell us about change. I'm a huge fan of this and incorporating this into the larger effort of trying to understand the environment and where it's going. The talk I'm going to be giving you today is, I don't know if it's a good or a bad example of that. We're right in the middle of it. This might be a distraction. This might really change how we think about the circulation of the ocean under global warming. In any case, it gives you some sense of the messy struggle between modern observations, predictions of the future, and studies of the past that in the end are going to help give us a more robust vision of the way the planet works and the way that it'll change. Okay, so I'm going to get to work. You guys eat lunch. I'm going to start out by describing the ocean as a sink for both fossil fuel CO2 and global warming heat. And this will bring to the fore the importance of the deep ocean. And Having done so, the next question that will arise is, how quickly will fossil fuel CO2 and heat, global warming heat, be carried into the deep ocean? This is a question of polar ocean overturning, the exchange of surface waters and deep waters in the high latitude ocean, and the response of this overturning to the warming that will be occurring due to the rise in CO2. And I'm then going to try to get some insight into how this polar ocean overturning responds to climate by looking at the ice age cycle. So I'm going to try to get some sense of the sensitivity to climate of overturning, specifically in the Southern Ocean, the ocean that surrounds Antarctica. And actually, I'll be even more focused than that. I'm talking about a region known as the Antarctic zone, which is the more polar part of the Southern Ocean that wraps right around Antarctica. So let's start by thinking about the uptake of fossil fuel CO2. Shown here is a famous record from Mauna Loa of atmospheric CO2 concentrations from 1958 forward in time. So we've got year on this axis down here, atmospheric CO2 concentration on this axis, and the measurements are here. We're somewhere off the page, off the chart over here, having broken through about 400 ppm CO2 in the atmosphere. Now, the dashed line is an estimate, a little bit of an underestimate, of how much CO2 in the atmosphere would have risen if nothing else had happened, but we had burned fossil fuels and changed the land to emit, and thus emitting carbon into the atmosphere. This is the CO2 concentration we would have in the atmosphere if that was the only thing we're having. We're just putting that carbon into the atmosphere. So what you can see is that the observations are on a lower trajectory, and the reason for that is that there are other places that carbon dioxide is going, other fates for carbon dioxide than just accumulating in the atmosphere. And thanks in large part, I better be careful about what I say, thanks in part to work done at Princeton, we now have a very good sense of what these other fates of carbon dioxide are. One is the land biosphere, and the other is the dissolution of CO2 in the ocean. And these are of about equal strength today. If you take any decade-long period, these sinks are about equivalent. But on the long term, dissolution of CO2 in the ocean is the ultimate fate for anthropogenic carbon dioxide. The land biosphere, while it is performing a terrific job as a temporary storehouse, there's no good reason to expect it to have a greater size, store a great amount of carbon after we're done with the human experiment of burning carbon, once we're all done with that. Whereas the uptake of CO2 by the ocean is an effectively irreversible process. What will happen is that CO2 is dissolving in surface waters are exchanging with the deep ocean. The deep ocean is incredibly vast, represents a huge volume, has a great deal of storage capacity for CO2, so the CO2 will make its way down into the deep ocean. And once down in the deep ocean, it will react with limestones on the seabed, and that will end up stabilizing the CO2 as bicarbonate, something that can't act as a greenhouse gas in the atmosphere. And this process is so efficient that if we were to just stop emitting carbon dioxide today, only about 5% or less of the CO2 would be left in the atmosphere if we were just to allow the ocean to do what the ocean wants to do. Take up CO2 into the surface, into the deep, and then react with limestones on the seabed. Okay, what about global warming heat? Well, we're emitting CO2 into the atmosphere. That CO2 is intensifying the greenhouse effect. And so the greenhouse effect is trying to warm the atmosphere. Okay? But the atmosphere overlies the surface ocean with which it's exchanging energy. And so as you warm up the atmosphere, the surface ocean demands to be warmed up as well. Okay? And surface waters are dense, they have a very high heat capacity, and so to warm up the surface ocean takes much more energy, actually, than it takes to warm up the atmosphere. And the energy excess that the Earth system can accrue in each and every year due to global warming is only so great. And so as a result, the role of the ocean is to slow down the rate of global warming. So just to document this, shown here are, for the period 1955 to 1998, is the heat added to different components of the ocean, of the Earth system, associated with global warming. And of course, what we really are thinking about when we're thinking about global warming is the atmosphere. But you can see that most of the energy went into the ocean. Okay. And we're also learning, well, so at this point I should mention that the estimates from model calculations is that the ocean's heat uptake has delayed about 30% of the atmospheric warming that we would expect for the CO2 rise that we've observed. And over the last decade or two, we've come to understand ocean heat uptake is a quite dynamic thing. So, for example, the relatively slow warming that we've had over the last decade is largely understood as a consequence of enhanced ocean heat uptake. Okay, so this is terrific. The ocean is the ultimate answer to anthropogenic carbon dioxide. In the meantime, is slowing down global warming because of its uptake of energy. What's the problem? Well, the problem is that the largest volume of the ocean, the deep ocean, exchanges only slowly with the upper layers of the ocean and thus with the atmosphere. So there's a great constraint on the rate at which the deep ocean can do its job for us. Shown here is an example of this. These are data, or calculations from data. This is a cruise track, oceanographic cruise track, across the Pacific from the south to the north, so south to north over here. This is depth in meters on this axis, so the surface is up here. And what's plotted is a calculation, and this also has deep Princeton roots, of the concentration of anthropogenic carbon in the water. And what you can see, the yellows and oranges are higher anthropogenic CO2 concentrations. What you can see is that most of the anthropogenic carbon, at least by 1994, was still trapped in the upper 600, 700 meters of the ocean. It had barely begun to be felt in the deep ocean. And the reason for this is that surface waters across most of the ocean are quite warm, and the deep ocean is cold, and that makes these waters less dense than these waters, and so these waters really don't want to mix vertically. Okay, so this traps the surface waters and the anthropogenic carbon right at the top. There are places in the polar ocean where surface waters become dense enough to exchange with the deep ocean, this overturning I was talking about before. And okay, sorry, I forgot to mention, I showed this picture for anthropogenic carbon. This is also true for global warming heat. It's also focused in the upper ocean in a very similar pattern. Okay, but back to where we're starting to exchange with the deep ocean. That deep ocean in this particular ocean basin, that exchange is occurring in the Southern Ocean, as I mentioned, as I introduced earlier on. Ironically, this has a signature here of sort of doming up the low anthropogenic carbon water up toward the surface, because we have this vast volume of deep ocean water that hasn't yet accrued a significant amount of anthropogenic CO2 being brought toward the surface. So what we want to do now is focus in on the Southern Ocean and understand it, understand this carbon and heat exchange a little bit better. Okay, here's our cartoon. Like many of these, this is going to look familiar to Jorge. Jorge, there he is. Okay, we've got the Antarctica over here. They used to be penguins. I did everything but remove the feet. The feet are still there. Just saw, and this is toward the low latitudes here. So we're looking at, and this is depth. So we're looking at a slab of the ocean. Okay. With the surface layer up here. So this is the overturning circulation of the Southern Ocean in very cartoon form. The blue arrows indicate the flow of the water, with waters coming up to the surface from the deep and then being entrained back into the interior, here as mid-depth water and here as abyssal water. Okay? And shown in orange and red are the flows of fossil fuel, carbon dioxide, and global warming heat. And you can see here they are in the atmosphere, and they're making their way into the surface ocean, and then this is a mechanism then for them to be folded into the ocean interior. Okay, so this is one of the critical high latitude regions that's doing the job of taking fossil fuel CO2 from the atmosphere and surface ocean and global warming heat and bringing them into the deep ocean. So if this overturning were faster, our expectation would be that fossil fuel CO2 and global warming heat would penetrate into the ocean faster. And with respect to both decreasing the rise in atmospheric CO2 and slowing global warming, this one might describe as a good thing if one were a human. Check on human. Okay. There are caveats here. One key caveat is that as you accelerate, there's another thing that happens in the Southern Ocean, and that's that naturally stored CO2 is actually vented from the deep ocean out into the atmosphere. And if you were to accelerate that overturning, this outward flow of CO2 would rise, even as this inward flow of fossil fuel CO2 would rise. And these would partially compensate each other. Exactly what the nature of the compensation is how perfect the compensation or imperfect the compensation is, we really don't know at this stage. But in any case, what we want to address now is, what do we expect to happen to Southern Ocean overturning, to Antarctic overturning, as we go into warmer climates due to the rise in CO2? Are we going to see such an acceleration of overturning, or will this overturning decrease in rate? Okay. So how will climate change affect Southern Ocean overturning? Jorge, maybe you should just come give this talk. This is a slide from Sarmiento et al. 1998, and what it shows is the results of a global warming experiment, its effect on ocean circulation, on polar ocean circulation in particular, and its consequences for carbon uptake into the ocean. So what's plotted here, these are years AD, and this is the vertical density gradient at high latitudes, north and south, of 30 north and south. So this is high latitude vertical density gradient. What is the density contrast between surface and deep waters? And what you can see so there's one model simulation where nothing is changed in the model, the climate forcing, and so the ocean basically remains as it is. On the other hand, in the warming experiment where CO2 is increased in the atmosphere, global warming occurs, and as a consequence of this, over time, the density gradient in the high latitudes becomes stronger. That vertical density gradient becomes stronger. And there are two very logical reasons for this. One is that you're warming the surface, but you're only slowly starting to warm the deep. Right? So you've warmed the surface, you haven't warmed the deep. That'll strengthen the density gradient in the high latitudes and elsewhere. In addition, in a warm world, we expect the low latitudes to do a more effective job of evaporating water off the surface ocean and transporting it through as water vapor through to the high latitudes and precipitating it out at high latitudes. And this is even evident in salinity, changes in the salinity patterns of the ocean from data. And so the second effect is that we are decreasing, we're freshening the high latitude surface at the same time as we're warming it. Both of these things are working together to increase the vertical density gradient at high latitudes as we go into the global warming. And so in this model, the result is that there's reduced Antarctic overturning under global warming. Okay. That stronger density gradient interferes with the surface to deep exchange that occurs in the Antarctic. Now, we've talked about the consequences of this for CO2 and for global, for such changes. If this were to occur for CO2 and for global warming heat, it may be that if we do see big changes in polar ocean overturning into the future, the consequences we notice the most are local consequences. So, for example, polar ocean overturning is a part of global ocean heat transport. So if polar ocean overturning changes, then this heat transport term will change. It'll lead to changes in atmospheric temperature gradients, so regional climate in high latitudes will be affected, wind and precipitation patterns will be affected, and the ice sheets will be affected. In addition, with regard to ocean life, the phytoplankton that grow in high latitude waters are as sensitive to the overturning as they are to anything else, like temperature. And so if you affect the overturning, you're going to affect phytoplankton productivity, both the quantity of phytoplankton and the types of phytoplankton. And this will then make its way up into the ecosystem. So polar ocean ecosystems are going to be influenced. This includes the fisheries and large marine mammals. Okay, so we've seen what the consequences of polar ocean overturning are for CO2 and global warming heat. We've seen an expectation put forward by model simulations for what will happen under global warming. We expect that overturning to decrease. What do we get when we look into the past? What do we look, and in particular what I'm going to be talking about are the ice age cycles. So what's the climate sensitivity of southern ocean overturning over ice age cycles? So, please.
For the, so you showed Corey's model, and it went out and started in 2000, and it got up by today, 2016. Is the data exists that shows the amount of vertical density changes are about what we're shown?
Yeah.
1.6 to 1.8.
So that's a good question. What are observations showing? So for the Southern Ocean, I think we are starting to see a freshening in high latitude surface waters. Something else is happening that will come up later when I talk, which is that the winds have strengthened over the 1900s as a partially due to consequence of global warming, partially as a consequence of the ozone hole. And these appear to be driving increased acceleration of one part of the cell. You're making me go ahead, okay? So stop it. Okay, yeah, I'm in charge, Daniel. Okay, so we'll come back to that later. So what I would say is that simulation that I showed you from the GFDL model is very common across the global climate models. This is well-shared behavior. One of the big caveats is the changes in the winds that the models are now trying to grapple with. Okay, the ice ages. Okay, what are the ice ages? Well, let's just talk about the last ice age, which was from about 65,000 years ago to 17,000 years ago. During the last ice age, there were extensive northern hemisphere ice sheets. So this is a cartoon showing the extent of those ice sheets during the last ice age. As a consequence of all this storage of fresh water on land as ice, sea level was about 130 meters lower. That explains why Florida looks so fat here. Its continental margins added to its land. The continents were about 9 degrees Fahrenheit colder. The tropical surface ocean about 5 degrees Fahrenheit colder. The cooling occurred in both hemispheres. It wasn't just a northern hemisphere phenomenon. There was more cooling at high latitudes than at low latitudes. There was less forest on land. And atmospheric CO2 concentrations were about 80 to 100 ppm lower in the atmosphere. So instead of pre-industrial values of the interglacial in which human civilization took off of about 280 parts per million, during the last ice age, CO2 levels were about 180 or 200 parts per million. It's not enough just to talk about the last ice age, though. We need to look at the progression of at the glacial cycles to really start to see what we can learn from them with regard to past climate. And shown here are 3 critical climate records covering the last 800,000 years. So today is over here. 800,000 years ago is over here. 2 of these records, the top and the bottom, come from ice cores, and the middle one comes from mostly it's a compilation, but comes from sediment records. And so what we have here in the middle is global ice volume plotted increasing downward such that it's like sea level. So if sea level goes down because ice volume goes up, with sea level plotted over here. Down here we have Antarctic temperature with warmer plotted up. Here we are today in our warm Holocene conditions, or prior to the human perturbations not shown here, but in any case. And then up here we have atmospheric carbon dioxide. Also higher CO2 concentrations plotted up. So pre-industrial levels during the interglacial in which we live, about 280 parts per million. Last ice age values, about 200 parts per million. So looking at the global ice volume record and comparing it to Antarctic temperature, this ice was built in the northern hemisphere, and conditions were certainly colder in the northern hemisphere whenever we had a maximum in ice volume. So, sorry, just to orient you here are based on the ice volume, we would define ice ages. So here's the interglacial in which human civilization took off, the last glacial maximum, the last ice age before it, the previous interglacial, the ice age before it, and so on, going back through the record. Okay? And we can see if we compare this record with Antarctic air temperature, whenever we have a lot of ice built up in the northern hemisphere during the ice ages, we have we have cold temperatures in Antarctica. Whenever we have minima in ice in the northern hemisphere, we have warm temperatures in Antarctica. So this speaks to this global nature of the climate changes associated with the glacial cycles. When you look at these records, I think you can feel that there's something cyclic in them. And indeed, our best understanding of the glacial cycles is that there are cyclic changes in Earth orbital parameters, which affect the latitude and the seasonal distribution of sunlight on the Earth. These changes engage aspects of Earth's climate feedbacks within Earth's climate and cause these glacial cycles. Okay, so ultimately, the orbital parameters are causing the glacial cycles. But when we look at the insolation, the solar input changes associated with glacial cycles, over a year, those changes are insignificant. Okay, so the orbital cycles can explain the pacing of ice ages, but they can't be the sole driver of these huge climate changes. What has to be happening is somehow these Earth orbital parameters have to be engaging positive feedbacks within the Earth system that then drive the actual climate change. And a good example of this is atmospheric carbon dioxide. When when we're in an ice age, CO2 is lower, and this will help to make colder conditions. And when we're in an interglacial period, CO2 is higher, and this will help to warm the climate. Okay? But then the question is, what's driving these changes of carbon dioxide? Why is CO2 going up and down as a function of climate or as a function of the orbital parameters that are encouraging these climate changes? I hope that was clear. Don't tell me if it wasn't. Okay, so one of the where the story starts here with regard to an effort to try to explain the CO2 changes that motivated the work that I've been doing with in the polar oceans involves what I lovingly refer to, and we all lovingly refer to, as the biological carbon pump. So let me explain how this works. This is the ocean's biological mechanism of carbon storage. Let's start out with the basic structure of the ocean. We have a sunlit, warm surface ocean underlain by a cold, voluminous, deep ocean. There's a strong temperature and thus density gradient between the two, and so they exchange water relatively slowly so far as the low latitudes go. We've got phytoplankton growing. There, the phytoplankton over there. And the chemist's view of the phytoplankton is there. This is organic matter that's being produced. This organic matter yields sinking organic matter into the deep ocean. So you're transferring organic carbon out of the surface ocean and into the deep ocean, where it's broken back down by bacteria to carbon dioxide and other stuff. And so this is effectively taking CO2 out of the surface ocean and the atmosphere with which it's exchanging, with which it is equilibrating, and sequestering that carbon in the deep ocean. Okay? Thus the biological pump. We are pumping CO2 into the deep ocean by biological means. So what sets the strength of this process, how much CO2 it sequesters in the deep ocean? Well, phytoplankton need other things like which we refer to as nutrients. And I'm just going to simplify this as just thinking about nitrogen, my particular favorite. The organic matter that sinks along with the nitrogen, and that nitrogen is also returned into the waters in the deep ocean. Here, this is shown as nitrate, which is the dominant nutrient form of nitrogen in the ocean. And because of the slow exchange with the deep ocean, the phytoplankton in the low-latitude surface ocean mine out all the nutrients, all the nitrate. And this then sets the amount of downward flux of organic matter you can have and how much carbon dioxide you can be storing in the deep ocean. Okay? So if you imagine just allowing this system coming to a steady state from some starting point, the amount of carbon that you will have stored in the deep ocean will be related to the amount of nutrients in the ocean by the stoichiometry of the sinking organic matter. Okay, well, this is where people first started thinking about the biological carbon pump, but pretty soon after this notion was presented, it was recognized that the polar oceans are a major exception that offer an additional dynamic. And so here are two slides that will help us think through this. So on the bottom we have the surface concentration of nitrate, that nitrogen nutrient. And on the top here, we have data on the chlorophyll concentration in the water, which tells us about phytoplankton abundance. So if we look down here at the nutrient map, the blues are very low nutrient concentrations. And so when I was telling you about the low-latitude biological pump, I was telling you about this region right here, this region of efficient use of nutrients. But as we go to the high latitudes, and especially the ocean around Antarctica, the Southern Ocean, we see very high concentrations of nutrients. Okay? So why is there this large burden of unused nutrient in the surface ocean in the high latitudes? Well, one hypothesis you could raise, I'll back up, is that the phytoplankton are just growing very slowly in high latitude waters. But that doesn't work because you can see here that phytoplankton abundances are highest in these high latitude regions. So phytoplankton are growing relatively quickly in these waters. So what this requires is that the supply of nutrients to the surface in the high latitudes is rapid. Okay? And we know what that is. That's the overturning circulation that we just discussed before. Okay? So these high nutrients are telling us about this overturning circulation that occurs in the Southern Ocean. Now, the phytoplankton are growing relatively quickly in high latitudes, but they're not growing as quickly as they could possibly be growing. And so oceanographers have spent a lot of time trying to figure out what it is that limits phytoplankton at high latitudes. And originally the focus was on light or on effects of downward pressure by zooplankton grazers. Whoops. But we've subsequently discovered the role of the trace nutrient iron in limiting phytoplankton in these waters. Well, what are the consequences of these unused nutrients in the high latitudes for carbon dioxide? We have nutrient and carbon dioxide rich water coming up to the high latitude surface, and the nutrients being incompletely consumed, and as a result, CO2 escaping back to the atmosphere. So this is our natural, I mentioned before, this natural venting of CO2 through the Southern Ocean. We now understand why it occurs. It's because nutrient and CO2-rich water are coming up to the high-latitude Southern Ocean surface, but the nutrients are not being completely scavenged again, and that allows CO2 to escape back to the atmosphere. So then the question becomes, if we want to think about how these sort of processes changed over glacial cycles, do we have a way of reconstructing the nutrient concentrations in the high-latitude surface ocean? So can we reconstruct surface nutrient concentrations in the past? And this is what we're trying to do with the isotopes of nitrogen. Okay. So let me take you through this. It's incredibly exciting. There are two isotopes of nitrogen, N14, the common isotope, and N15, the rare isotope. We're going to be talking about the N15 to N14 ratio of different sample types. And in case I go into my usual lingo, a high delta N15 is just a high N15 to N14 ratio in a sample. Okay? The relevant dynamic here is that as phytoplankton assimilate nitrate in the surface, they preferentially assimilate N14 nitrate in proportion to N15 nitrate relative to the concentrations that these two forms of nitrate occur in the water. Or in other terms, they fractionate between these two forms of nitrate. Let me show you the consequences of this in the modern Antarctic, coastal Antarctic. So plotted here are data from different times of year in the Antarctic zone. We have depth on this axis. So we're in the deep ocean down here, and up here in the upper 100 meters, during the summer, this is where phytoplankton will grow. What's shown here is the nitrate concentration in the water. And over here, the N15 to N14 ratio of the nitrate increasing to the right. Okay? So these data are from different parts of the Antarctic, but the key thing is that the samples were taken at different times of year. The yellow and the gray were taken during the winter or just at the end of the winter, and the red, green, and blue were taken during the summer. And so what you can see is that phytoplankton are assimilating nitrate and thus drawing down the nitrate concentration in surface waters over the course of the summer. As I told you already, they're not doing it completely in the Southern Ocean. So there's plenty of nitrate left in the surface, but they are drawing it down during the summer. Associated with this drawdown of nitrate, there's a rise in the N15 to N14 ratio of the residual nitrate, the nitrate that's still there. Okay? Because N14 nitrate has been preferentially consumed. When you generate a plot that allows us to better compare the nitrate drawdown to the nitrate N15, N14 ratio, we have consumption, the degree of nitrate consumption increasing to the left here, and the N15, N14 ratio of the nitrate rising, and you can see there's a consistent relationship across these data. Okay. Now, phytoplankton are driving this pattern of N15 elevation as nitrate is consumed, but they're also consuming this nitrate as it's changing in its N15, N14 ratio. And so phytoplankton such as the diatoms, their biomass will reflect the N15, N14 ratio of their biomass will reflect this change in nitrate. So the N15, N14 ratio of their biomass will increase with progressive nitrate consumption. And similarly, the zooplankton, such as foraminifera that eat those things, will record that signal as well. N15, N14 increasing with progressive nitrate consumption. And the reason I'm interested in these two particular types of phytoplankton and zooplankton is that they generate fossils in the sedimentary record. So if you go to Antarctic sediments, much of the sediment is composed of diatom fossils. There are foraminifera throughout the global ocean that can help us. And moreover, the phytoplankton and zooplankton, the debris they produce that sinks into the deep ocean, feeds a deep ocean ecosystem. And so we study things like deep sea corals that leave their fossils on the deep sea floor, having eaten the sinking organic matter from the surface. And our goal in all of this then is to measure the N15 to N14 ratio of shell-bound organic matter. If it's higher in the past, it would suggest that nitrate was more completely consumed in surface waters at times in the past. Maybe I should have just said that last sentence. Anyway. Okay, so I'm going to show you just a little bit of data to give you a feel for what they look like. I'm going to focus on sediment core from here in the Antarctic zone. These are data from Anja Studer, and what we're specifically going to be looking at is diatom-bound nitrogen isotopes, along with some other records in that sediment core. And then I'll also quickly say something about N15, N14 data generated by Tony Wang as a part of his thesis in this region here in the Drake Passage. Okay, so here's the sediment core from the Pacific sector of the Antarctic. In fact, there we have age on this axis. So here's the modern again over here, 200,000 years ago over here. So the two upper records are not actually from the sediment core, that you've already seen them, or them going further back in time. This is the Antarctic air temperature reconstruction from an Antarctic ice core. And this is the atmospheric CO2 record, also from Antarctic ice cores. And so the interglacials, you can barely see the colors here, but the interglacials are these times of high CO2 and warm temperatures in Antarctica here, and the ice ages are in this period here and here, okay? And Anya has gone back through, and so this is an interglacial, this is another interglacial, and this is working back toward yet an earlier interglacial as we go further back. Okay, so now to the stuff actually in the sediment core. The first thing I'm going to start with is the stuff on the bottom. And these are two measures of the productivity in the surface ocean back through time. One of them, the more easy one to explain, is the diatom flux. It's just the accumulation rate of diatoms on the seabed going back through time. And what you can see here is something that people have seen many times previous from Antarctic sediment cores, which is that productivity is lower during the ice ages than it is during the interglacials. So productivity high in the interglacials, low during the ice ages. But what about surface nutrient concentration? Okay, sorry, productivity ice age, lower. So here are the diatom-bound nitrogen isotope data. And the N15, N14 is plotted increasing downward, so higher nutrient concentration in the water would be plotted upward. Okay? Higher degree of nitrate consumption downward, higher leftover surface nitrate concentration upward. There are two different records here. One is the black is of all the diatoms that we could extract from the sediment. The other is a fraction of those diatoms, removing one special form of diatom. You can think of these here as just analytical replicates, and gives you some sense of how well we're able to make these measurements back through time. But so what do we see? We see even though productivity is lower during ice ages, we see N15, N14 ratios that are higher. That would suggest a more complete nitrate consumption from surface waters during the ice ages. So degree of nutrient consumption higher during the ice ages. Now this is odd. Productivity is lower during the ice ages, and yet the degree of nitrates consumption, the amount to which the nutrients have been consumed, is greater. How do you do this? Well, there's one answer, and that's that you reduce the nutrient supply into the system. Where do these nutrients come from? They come from the subsurface in this overturning process. So what this points to is a decrease in surface-to-deep exchange in Antarctic surface waters during ice ages. As some source of confidence to this, I'm showing you here now the N15, N14 data from deep-sea corals in the Drake Passage. And here you also see higher N15, N14 during the glacials, during the last ice age, increasing into the current interglacial. And this is comforting in two ways. First of all, the deep-sea corals live on the seabed, whereas the diatoms live in that upper 100 meters of the surface ocean. So the uncertainties associated with these paleoceanographic proxies is very different. So we're getting the same answer from both. Feels good. In addition, the corals come from within the Drake Passage, and a lot of the Antarctic needs to squeeze through the Drake Passage. So a lot of the Antarctic needs to squeeze through the Drake Passage as it circumnavigates Antarctica. And as a consequence, those corals should do a pretty good job of integrating all of the conditions in the Antarctic. So even though our sediment records are often from pretty close to the polar front, the northern edge of the Antarctic, these deep-sea corals seem to be telling us that this pattern applies to the entire Antarctic. Can't be sure of that yet, but this is the first positive sign, that is true. Okay, so what have I just said to you? This is the nutrient map that we started out with. High nutrients in the Southern Ocean are reflecting the high nutrient supply to this region, the rapid overturning that occurs there. And what I've told you is that our nitrogen isotope measurements would suggest that these nutrients were at lower concentrations during the last ice age. These would be less orange, more light blue. Okay? At the same time, productivity does not seem to have been higher in the Antarctic zone during the last ice age. And so the only way to explain this observation is that there was reduced surface-to-deep exchange in the Antarctic during the last ice age. So under a colder climate, less surface-to-deep exchange. less Antarctic overturning, if you will. Now, that might seem all hunky-dory, but climate models run under ice age conditions give exactly the opposite answer. Exactly the opposite. They've never done anything different. Antarctic surface deep exchange is always enhanced during ice ages in climate models. So I'm nervous, but I'm also kind of excited. Maybe we've learned something that's going to change the way we think about ocean circulation. One of the ways we're trying to grapple with what we've learned from the Antarctic data is to see if it's reproduced or has any parallels in the other polar ocean regions. And it turns out that in the subarctic North Pacific, a system that has many similarities to the Antarctic, from the foraminifera, Abby Wren has observed the same type of change, evidence for reduced surface to deep exchange during the last ice age. Some of you will be familiar with the North Atlantic deep water changing, North Atlantic deep water formation. If you've never heard of North Atlantic deep water, don't sweat it. But if you have, you're familiar with the idea that it's changed over glacial and interglacial cycles, and specifically that North Atlantic deep water formation declined during ice ages. And people have come up with various hypotheses for why this might occur. We're exploring the possibility that it's more related than people would have thought to the changes that we're seeing in the other polar ocean regions. So what we've found in the Antarctic may be a global phenomenon. And this, we think, will help us to get at the big question that this leaves behind is, if we're right and the model simulations have something wrong, what is the mechanism? What is the physical mechanism for that? Okay, what are the consequences for CO2 and for the future? So first, glacial and interglacial CO2. This is a cartoon that we could draw for the current interglacial before human monkeying around. We've got a surface ocean and a deep ocean in the Antarctic zone. Nutrient and CO2-rich water are rapidly coming to the surface. Phytoplankton are only consuming a fraction of those nutrients, and so a lot of unused nutrient is descending back into the interior. And this means that a lot of carbon dioxide, excess carbon dioxide, that the low-latitude biology did the hard work of storing, has been leaked back out to the atmosphere in our interglacial world. During the last ice age, however, this overturning circulation declined, and the net effect is to decrease this leakage of CO2 out of the Antarctic during the last ice age, and can explain something like 40 parts per million of CO2 decline during the last ice age. And it may say, hey, you told me it was 80 to 100 ppm lower during the last ice age. And that's right. This doesn't look like it can explain the entire signal. But it can explain a fair chunk of it. Okay, but let's stretch this a little bit further. Here we're going from a case of cold conditions to warm conditions. Instead of thinking of this as the last ice age and the current interglacial, let's go out on a limb and consider the possibility that instead we're talking about going from today's conditions to some global warming future. Okay? So then this would be our cartoon for today, much like I showed for the interglacial that human civilization took off in. And then over here would be the future global warming scenario, in which if we have the same relationship between temperature and Antarctic overturning, we would expect stronger Antarctic overturning. So what are the consequences of this if this is in fact how it works? Going from today into the global warming future, we would expect uptake of global warming heat to accelerate. With respect to carbon dioxide, the uptake of fossil fuel CO2 should accelerate. The natural release of CO2 should also accelerate. And again, we have this question of how exactly these two are going to compete with one another in terms of the net effect on CO2. Most suggestions at this stage is that the net effect will be that CO2 uptake by the ocean will accelerate under this scenario of overturning circulation. Okay? We hope to try to test this particular issue by looking at multiple interglacials, comparing different interglacial periods in detail. So if you take this as I've said it, you might consider this as good news. More rapid uptake of global warming heat, potentially more rapid uptake of CO2 from the atmosphere under global warming. But the problem, again, is just a very strong disagreement, apparent disagreement with the models. Now, in this case, there are various ways that one can go. One can say, well, we're looking at a process that applies on a 1,000-year time scale. The global warming simulation is something that applies on the time scale of decades and centuries. Maybe they're just two different time scale. This is the issue. We're just comparing the two different time scales. The thing that makes me not so swayed by that is that I've already told you about what the models do during ice ages. Those are 1,000-year simulations, and yet we still have the same sense of disagreement. The models under colder conditions have more rapid Antarctic overturning. During warmer conditions have... did I just mess that up? Yes. No, I didn't. Models during colder conditions have more rapid Antarctic overturning. During warm conditions have reduced Antarctic overturning. The data we have going back to colder conditions suggest the opposite. Okay, I think you got my point there. Yeah. Whew. Another issue here is, in terms of addressing what the consequences for CO2 will be, we need to understand what the biological response of the Southern Ocean will be in terms of how much if this overturning circulation does in fact accelerate into the future, how big the outward green arrow will be, and thus how much it'll counter the fossil fuel term. And as I mentioned before, there are strategies for using the glacial cycles again to try to sink our teeth into that question. Okay, so I'm going to summarize now. The ocean is the eventual sink for fossil fuel-derived CO2. The added heat from global warming is dominantly going into the ocean, which is slowing the warming. So the ocean's doing good work for us with regard to both fossil fuel CO2 and global warming. The rate and carbon heat uptake into the ocean depends on the overturning of the polar ocean, the future of which is uncertain. And here in black is the stuff from our ice age studies. Overturning in the Southern Ocean was reduced during ice ages and it increased during the warm interglacials. This may indicate that carbon and heat uptake into the ocean will accelerate into the future. Broader messages here for those of you who rarely come to Geo Hall, or at least that side of it. No, this side of it. Oh, whatever. Okay. The ocean is central to climate and climate change. So it explains why there are so many, if you're going around campus, why there are so many people who are studying the ocean. The ocean is a really important part of the climate system. We can't think about climate without thinking about the ocean. In addition, the polar ocean regions provide access to the deep ocean. And that makes the polar oceans particularly important in these questions of global warming heat and fossil fuel CO2 uptake. And it explains why there are big measurement and modeling programs at work on Princeton campus. SOCOM is a good example. This is a little bit of an aspiration. Studies of the past climate are necessary. They're really important additional complementary information to modern studies. The problem has been that we just haven't had the tools to really do this. But we're getting better and better. Human ingenuity is not showing any signs of disappearing. And that holds great promise for our ability to reconstruct past climate changes and for us to use the past climate changes to tell us about where we're going into the future. Thank you. Where Southern Ocean overturning does accelerate in the ice ages.
In other words, I guess there's a bit of circularity that you're using nutrient data to tell you the circulation slowed down and it was more depleted. I'm wondering, is there any independent data that confirms that the circulation indeed did slow down? Because an alternative scenario is that the circulation increased and the efficiency of removal of nutrients also
Yeah, so it wasn't circular. I'm relying on the coupled use of the nutrient consumption and the export production proxies, right? But the export production proxies you don't want to hang your hat on them. Not all phytoplankton make fossils that are buried in the sediments. We have a limited number of tools for export production. So I agree with your basic question, which is, or I'm with you on this basic question, which is, are there other things that are telling us the same thing? Radiocarbon in the deep ocean during the last ice age does appear to have declined, radiocarbon content, in volumes that today are not rapidly ventilated by North Atlantic deep water, so you can't explain in terms of North Atlantic deep water formation changes. You yourself know that the C13 distribution of the glacial ocean as reconstructed by benthic foraminifera is consistent with a reduction in Antarctic overturning. So that's Eun-Young's, that's in Eun-Young's simulation that you know about. The other tools you have are less clear cut. So there's deep ocean oxygen. Deep ocean oxygen also decreased during the last ice age. That indicates that indeed there was more respired carbon dioxide down there, just as you would expect if the Southern Ocean was a reduced leak of CO2 to the atmosphere. But it doesn't tell you whether that was due to increased biological production or reduced surface to deep exchange. There are efforts, so this kind of goes on and on, Jorge. And what I would say is that we don't have a better tool yet to tell us about surface to deep exchanges than what I've shown you.
Normally when modelers have a result that experimental data disagree with, modelers revise their models. So you haven't told, unless I missed it, you haven't told me what's in the models that could be removed in favor of something that would create the opposite sign.
Yeah, I haven't told you. I mean, to describe the physical mechanism, I'd need another talk. Okay? No. So
one short paragraph.
Yeah, no. So, but this is the problem when I make a joke, I lose my focus. So, the first evidence for this reduced surface to deep exchange from data started to pop up in the late 90s. And since that time, people who think largely about ocean circulation have been starting to try to think of ways that this could work. And there are a lot of very smart people who are doing this right now. So Robbie Togweiler suggested that maybe you could explain reduced Antarctic overturning by reducing wind-driven upwelling in the Antarctic, which would allow the halocline, the fresh layer, to have a longer residence time, to strengthen, and to reduce surface to deep mixing. Models don't usually get the winds to weaken or to move as Robbie exactly wants them during glacial simulations. Maybe they're just not doing a good enough job. Okay? So there's one example. Another is people are thinking about how you remove deep water from the ocean. So one thing that affects the rate at which you form new deep water in a place like the Antarctic is how rapidly you get rid of dense water in the deep ocean. And this is influenced by the vertical mixing in the ocean, or the mixing across density surfaces in the ocean, which is influenced by where the biggest density gradients are relative to the topography of the ocean, across which mixing is easier. So there are people this is where I would go from here. I would set up for you about 4 or 5 suggestions that have been made. But here's the deal. The models don't simulate these things by themselves. Okay? My particular interest in this is to try to use data to help us with these different hypotheses. Some things work in the Southern Ocean, but then don't help to explain the North Pacific data. I want a hypothesis that can explain all of my observations. Gene?
So my understanding of the isotopic data is that you're able to track fractional consumption. So you have a percent change, essentially. And if I understood what was happening is you're making an assumption about the nitrate content. I could explain the data by just dropping nitrate concentration by a factor of 50%.
The deep nitrate concentration.
Nitrate having the exact same amount consumed, and I would then have a larger isotope effect that is observed.
Right. So, a fair amount of... so this is a really interesting question. What sets the nitrate concentration in the deep ocean over time? It's a difficult thing to reconstruct, but we can study nitrogen fixation and denitrification, the processes that are adding and removing nitrogen from the ocean. And from all of the, I'm a strong believer, based on data that I've produced and other work that I've seen, that nitrogen fixation is doing a pretty good job of setting the nitrogen reservoir of the ocean to the phosphorus reservoir of the ocean. Okay? Now the phosphorus reservoir, so that now you have a question of how much can you change the phosphate reservoir of the ocean during the last ice age. And the residence time, people have done residence time calculations for the phosphate reservoir in, when Philip Froelich did it with Michael in the 80s, the number was near 100,000 years, 80,000 years, something like that. Kathleen Ruttenberg took another shot at it. The estimates, she suggested maybe it was as low as 20,000 years. Then subsequent work pushed it back up toward 80,000 years. So right now it looks like phosphorus has a relatively long residence time in the ocean, too long to explain what we see across deglacial transitions. Okay? Further, we don't really have a mechanism for changing the phosphate reservoir a lot on the timing that we see big CO2 changes. Now, you could say, no, it's not whole ocean phosphate or nitrate change. It is regional changes in the nitrate concentration in that particular deep reservoir. And that, I think there are strong arguments against, based on just looking at delta C13 data, using them to tell you something about regenerated carbon fields and variations among those waters. So yeah, I know, if I change the upwell nitrate concentration, if I bring it down a lot, I could start to do this. But I don't think that's in the cards. Oh, I'm sorry.
Grant, I have a quick question. You raised iron elimination or light elimination early on in the model to explain surface concentrations, and then you dropped it from the story. Is there a story there?
Yeah, so what's the role with iron here? How do I explain... Okay. For the Antarctic zone, I need to explain why decreasing the overturning, let's go that way, will lead to higher degree of nitrate consumption. If you believe that all of the iron came with the deep water, then as you decrease the overturning rate, the iron will decrease, the rate of iron supply will go right with the rate of nitrate supply, and nitrate consumption should hold constant. There are two options for that. One is that you have some non-trivial amount of iron coming in from the top, from the atmosphere or from other shallow inputs, that when you decrease the supply from below, that iron input is there, so the net iron to nitrate supply ratio rises. So that could explain the Ice Age data. There's another idea that I like more, which is, and I've been talking to Francois about a little bit, which is that in iron deplete nitrate-rich regions, iron is more efficiently cycled in the surface ocean than is nitrogen. And the consequence of that is if you just increase the residence time of that those surface waters in the Antarctic by decreasing the overturning, you'll be able to draw down more nitrate simply because the iron will stick around for longer. That said, the other half of my 80 to 100 ppm CO2 change, I do believe, is coming from increased iron fluxes to the more northern part of the Southern Ocean. This is an iron fertilization story, which explains a totally different set of observations from the northern edge of the Southern Ocean region that I haven't talked about at all today. And if you would ask me how this works over the 3 million years of glacial cycles, what I'd say is, we know that there are 40 kiloyear cycles, 40,000 year cycles over much of the first part, up to about 1 million years ago or so. And that's the time when you start seeing big iron flux increases to the ocean during ice ages. And that over that first part, you just had the dynamic I've been telling you about, which is changes in Antarctic overturning, driving CO2 up and down by 40 ppm. And then when you get to this time when you start getting large ice age iron fluxes to the ocean, you add an additional 40 ppm, deepen ice ages, and switch to a different periodicity of 100,000 years.
One more question.
I have some question about the iron context or iron fluxes.
Put a lot of emphasis on carbon dioxide and nitrous oxide. What about, say there was 1 billion vehicles on the Earth, each one has a radiator attached to the engine. That's dissipating a lot of heat and adding to global heat also. Is there any measurements or studies on the dissipation of heat from radiators?
Yeah, so I've never done these types of calculations. People have done them. And those sort of, you do see those kind of effects in the form of island effects, city island effects. You know, this was the global warming skeptics' favorite thing to explain global warming, up to the point that we started having satellite data. You know, so, that's only part of the heat island effect. That part is trivial in the global heat budget. Is what I think. I could get an expert to tell you.
Heat is 10 to the minus 4 of solar.
Say again?
Anthropogenic heat.
I was just about to say it's 10 to the minus 4 of solar input.
Anthropogenic heat is 10 to the minus 4 of solar.
Thank you.